All right, we'll go ahead and get started. Welcome in, everyone. Greetings. Happy Friday. I hope everyone's doing well. I am Professor L, and this is going to be a math stream for math tutoring or math help. So if you have a math problem you would like to see worked out, you're welcome to put that in the chat. And in the meantime, I am going to be working on my board just informally. I've planned to work with the exponential function today, and forgot to tuck my stool back in there. So I'll be working, with the exponential function, and we'll just see how it goes. And moving on from conic sections, so I'm not going to review this one. Just go ahead and erase. Exponential functions are really important in math modeling courses. What they do is they model growth and decay. So bacteria growth models, any kind of organic growth model or decay, the exponential function models that very well. And so that's usually the applications that it appears in algebra and math courses. And then out of the exponential function, we have the logarithmic functions, because they are they're essentially inverses. So with the natural log being the inverse to the e function, and we got into that in my curriculum when I taught the pre-calc for community college. So we have this function. It's the exponential function, and I'll go ahead and title it. Okay, and what we're talking about is an exponent. So this function is going to model any other math concept or math function that has an exponent. It's going to follow this, and it's a b to the x. And where let me see what it says here. I have it pulled up. So a cannot equal 0. And I'm just going to write this out real quick because we're going to evaluate this function, and we're going to graph f of x equals, we'll do 5 to the x. We'll try that one. Well, I don't want to make it that big. So we'll do 2 to the x. That'll be sufficient. So we'll have our table, and we're just going to get a general behavior of this graph looking at my favorite 3 points. We'll do -1, 0, and 1. So it's saying if b is greater than 1, it's a growth. Well, we'll talk about that later after we get these graphs sketched. We'll talk about all that in a minute. And it's me trying to prepare a little bit, just having a concept in mind, and I can't believe I didn't actually, I knew what I wanted to graph, but I didn't actually have an example, so I had to pull that 2 to the x out off the top of my head, and I'm really not creative when it comes to coming up with examples. But if we manipulate this 2, it'll work. So, all right. So what all we're doing is we're taking this function and we're plugging in the same method, this same brute force method of graphing, where you take a a set of values in the domain, you plug into your function, and then you get the range, and then that you plot the points, and then it shows you the behavior and what your graph looks like on the Cartesian coordinate system. So when I take this function here, f of x equals 2 to the x, and I plug in -1 for that, it's going to be 2 to the -1. And then I have to remember my exponential rules. When I have a negative exponent, that means I'm taking this value and I'm moving it to a denominator. That negative exponent represents the denominator. So it looks like f of -1 is going to be 1/2. Again, that's your exponential rules. And I think I had, I'm pretty sure I have a picture of the exponential rules, but I don't need them right now. All right. And then again, we're taking that function when x is 0 and looking at what's going on. And you need your exponential rules for this. So it's like I take for granted the math because people might not be aware of the exponential rules, but there is a set of rules whenever you're dealing with algebraic expressions and simplifying and evaluating them if they have an exponent. So anything raised to the 0 power is equal to 1. So that's one of the rules. So if you raise something to a 0 power, it's the quantity 1. And mathematically, that can be proven pretty easily. Anything divided by itself is equal to 1. So if you have 2 to the first power, and divided by 2 to the first power, and then that negative exponent rule becomes negative in the numerator. That's 2 to the first power times 2 to the negative first power. And whenever you have two numbers that have the same base, you're multiplying them, you add the exponents. So when you add 2 to the first minus 1, you get 2 to the 0, which is 1. And then this is how it's shown, that anything raised to the 0 power is equal to 1. So we have this function on here. And then one more evaluating f of 1 here is going to be 2 to the first power. 2 to the first power is just 2. Okay, which is 2. All right, so we have a couple of ordered pairs here we can sketch. And we'll say -1, 0, and +1. And at -1, I'm at 1/2. So if this is 1, we'll say that's 1/2. I have this ordered pair here. I have 0, 1. And let's see, I have 1, 2. We need one more value up here. And then if I wanted to, just for fun, we could go ahead. But what this graph is doing, it's curving upward at such a fast, rapid pace, it is increasing, that by the time we get to 2, we'll put some more values in here. We're already at 4. If I plug in 2, and we'll do one more just for fun, 3. We have f of 2 is going to be 2 to the second power, which is 2 squared is 4. So we're already at 2, we're already way up here at 4. So let's raise the graph up a little bit. So 3, 4. Okay, very good. And then if we went out here to -2, let's do that. It needs to be a little bit further out. -2. One more. F of -2. This is 2 to the -2. So this is going to be 1 over 2 squared. Look at my different 2's. What's going on with me? All right, 1 over 4. So at -2, let's see, we didn't put these points on here. At 2 over 4, we didn't do 3 because 3 is getting too hard. It's not going to be on the graph. So I went ahead and did -2. And at -2, we found that we were at 1/4. So what's going on here? Let's see, that would probably be 1/4 right here. Is we've got